Good afternoon and welcome to my presentation. My name is Premankur Banerjee and I am here to present our paper, The Impact of Airflow and Multisensory Feedback on Immersion and Cybersickness in a VR Surfing Simulation. Airflow to simulate wind in virtual reality has shown to enhance user immersion and mitigate cybersickness, particularly in virtual motion simulations. Multisensory feedback, on the other hand, specifically haptic cues and motion-coupled devices, significantly enrich user experience in VR. Now, while both constant and airflow, synchronized with speed of movement in VR, have individually been compared against a no airflow condition, direct comparisons between constant and variable airflow have not yet been explored. Neither has the effect of airflow been tested when users are actively physically engaged in the system. Furthermore, relative contribution of airflow, vision, and motion or kinesthetic cues on mitigating cybersickness and increasing user immersion in VR also have not been explored to the best of our knowledge. Our system comprises of a surfboard mounted onto a 6 degree of freedom motion platform, a safety harness to allow users to adopt various postures on the surfboard, and the simulation which is developed in Unity 3D and rendered on MetaQuest headsets. Looking at the video, as you can see, the movements along the 6 degrees of freedom mapped to the motion platform corresponding to the virtual surfboard movements in VR. Users navigate the simulation using a hand paddling technique in which their hands are tracked by the headset. The system detects when the hands are below the virtual water surface and applies appropriate reaction forces and torques to the surfboard based on the hand velocity. Looking at the video, you can see that the longitudinal and lateral hand movements propel the surfboard forward, and paddling with either hand makes the surfboard turn left or turn right. And for the airflow setup, we secured a fan to the front of the surfboard by using cable ties passed through 4 holes drilled into the surfboard. This ensured that the fan would remain stable throughout and that users received wind flow even if the surfboard was turning or tilting. The fan's dial was adapted to allow for continuous regulation by connecting it to a servo motor, which also allows the Arduino to control the speed of the fan through the rotation of the servo motor. An interesting observation was that the wind speed from the fan did not change linearly with the change in fan dial's rotation. Therefore, we had to establish a nonlinear relationship between the speed of movement in VR and rotation angle of the fan's dial. We used an air data multimeter to measure wind speed. We collected the wind speed recordings at approximately the position of the user's face when they were seated on the surfboard. Now, wind speed data was collected at 5 degree intervals from 0 degree to 270 degrees, which is the range of motion of the servo motor and also the fan's dial. And at each angle, the wind speed was recorded 10 times and then averaged out, which resulted in a total of 540 measurements across all angles. This was done to mitigate the influence of external factors on the measurement. The data shows a nonlinear relationship between fan dial rotation and wind speed, which was approximated using a logarithmic curve. The speed of the surfboard velocity in VR was linearly mapped to the range of wind speed because the maximum achievable surfboard speed in VR was 15 meter per second, and we only had a wind speed of 4.5 meter per second maximum. The research questions that we have answered in this paper are: what is the impact of two types of airflow, constant and variable, on overall VR immersion and cybersickness? Does the type of airflow influence immersion and cybersickness differently, if at all, when users are actively physically engaged in the virtual environment? And what is the relative contribution of each of the 3 sensory feedback conditions, airflow, vision, and motion, on perception of acceleration, mitigating cybersickness, and increasing immersion in VR? The first 2 research questions were answered by the first user study. Here, The task was to paddle to a certain location marked in VR and to try to catch waves. In the passive condition, the operator controlled the surfboard to match the wave's speed, while in the active condition, participants paddled to catch the wave themselves. Each condition included 2 wave-catching attempts, followed by a short break before switching conditions, and all the conditions were counterbalanced across all participants to mitigate any order effects. After each condition in the experiment, participants filled out the Immersive Experience Questionnaire and the Simulator Sickness Questionnaire. And here are the results from 28 participants. We conducted a two-way ANOVA to examine the effects of user mode and airflow. Analysis showed that participants felt most immersed and least sick when actively engaged in the simulation with variable airflow, while passive control with constant airflow led to the highest cybersickness. The findings suggest that variable airflow had a stronger effect on nausea, while active control reduced disorientation. In the second user study, which helped find the relative contribution of the 3 sensory feedback conditions, we had 4 conditions. M1, or the condition in which all the sensory feedback modalities were present together. M2, where the fan was turned off to stop airflow. M3, in which no visuals were rendered, just a black screen. And M4, where the motion feedback from the motion platform was disabled. And we conducted 2 experiments. Experiment 1 examined how well participants could perceive different levels of acceleration on the ocean surface, and they experienced 3 acceleration levels, low, medium, and high, under each sensory feedback condition. And experiment 2 explored the individual contributions of vision, motion, and airflow to immersion and comfort in our VR surfing simulation. The results show that both acceleration levels and sensory feedback significantly influenced perceived acceleration. Motion cues from the platform played the dominant role in acceleration perception, with their absence reducing accuracy. Significant interaction effects between acceleration levels and sensory feedback conditions were observed, and that indicate that some modalities might have been more influential under specific acceleration levels. Removing visual and motion cues significantly reduced immersion, with the absence of vision having the most pronounced effect on immersion or immersiveness. Airflow had a smaller impact, though its presence contributed to overall realism. The highest immersion levels were achieved when all the sensory modalities were synchronized together. Cybersickness symptoms were negligible and shown to improve in certain participants when all of the feedback conditions were present together. Removing motion cues led to the highest discomfort and disorientation. These tables depict the values of immersiveness and cybersickness across the conditions. The key takeaway here is that removing visual or motion feedback has the biggest impact on immersion, with visual cue removal causing the most significant drop across all categories. And removing motion feedback causes a severe increase in cybersickness. Summing up, synchronous airflow with VR movement speed increases immersion and reduces cybersickness as compared to the constant airflow conditions, even with active user engagement. Motion feedback is crucial for acceleration perception and minimizing discomfort, while airflow significantly helps with nausea. Visual feedback plays the strongest role in immersion. Therefore, in conclusion, while multisensory feedback modalities have the potential to significantly enrich user experience in VR, its effectiveness is highly dependent on the proper alignment and integration of sensory cues. Current limitations of our work include a restricted wind speed range and single direction airflow. Multi-directional airflow might contribute to a richer sense of immersiveness and reduce cybersickness. Future work will explore additional sensory cues such as audio, temperature, and scent, along with a larger longitudinal studies to assess adaptation and demographic effects. Extending these findings to other physically engaging VR simulations will further validate the generalizability of our results. Thank you for listening to my talk, and this is a small video that shows our our VR surfing simulation in action. Thank you.